about the smart contract vulnerabilities and solutions. So till date, you have seen the different blockchain platforms. And in further lectures, you will see the different applications based on the blockchain and smart contracts. Today, we'll see that security risk of the smart contracts. So already we have seen that what is smart contract. It is executable code, can be called as a byte code, which is stored on the blockchain transactions. So if you see the traditional contracts where two parties are meeting, they are agreed to their terms conditions, and the contract is being, it is like paper-based contract, so a contract is being created by the third party and the execution is taking place. Where there are certain challenges of such traditional mechanism of writing the contract and executing, because it is like paper-based contract. And it is difficult to build the trust among the parties. Again, it is affecting to the scalability if number of participants are growing. So here, blockchain-based smart contracts are helping well. Such smart contracts includes the functions, conditions. So the functions and conditions will be applied as per the user requirement and business logic. So whenever a user is performing a transaction, the conditions will be applied on the transaction, and upon the fulfillment of those conditions, contract is being executed. Such contracts are deployed on the blockchain. So obviously it will give the immutability of contract. And each node is having the copy of this contract. So availability of the contract is also implemented, or I can say availability is also achieved using the smart contract. So if you see the right side of these smart contracts where two parties are meeting and the contract is being uploaded on blockchain and the execution is taking place. There is no intermediary between these two parties. So obviously it will reduce the intermediary cost also. If you see on Ethereum, the smart contract execution process where you can see the two parties are meeting, they are agreed to their terms conditions. So whatever terms conditions they are creating, they will reach to the developer. Developer will convert those conditions in terms of the code. That code will be compiled. The compiled code is being converted into the byte code, and such byte code based I can say contract can be executed over the Ethereum virtual machine. Here miners are playing a major role in the execution of the contract, and this contract is being deployed on the blockchain in the form of the hash value of that contract. So whenever any event will trigger, that event will trigger the contract, and based on the contract condition, payment will be released and it will go for the verification. So this is the overall process of the smart contract execution. This is already covered by the Professor Roman in lecture 13, that contract contains the executable byte code. It is created with a blockchain transaction. So the contract is being stored on the blockchain in the form of transaction. And as we have already seen that transaction on the blockchain are the immutable. So such contracts are immutable. So nobody can modify their terms conditions. Contract is having the internal storage. So in the form of variables, you can add the values. So internal storage is also having. Contract execute when triggered by the transaction or any other contract. So a contract can be called by a user who is initiating a transaction, and that contract can call another contract by initiating the function call. So ultimately we can say that contract is also one of the kind of node which is calling another contract. So obviously each contract should have its own public address. As we have already seen that when one party would like to send some currency to the another party, the currency transfer is taking place based on their wallet ID. because it is like public address. So each contract is having its own public address through which that contract is being called. And each contract is limited by its, I can say, in case of Ethereum, it is like gas limit. So whenever you are calling that contract or whenever that contract is calling another contract, the gas value should be mentioned. So you must have to, the user must have to spend some ether to call the contract. Similarly, if a contract is calling another contract, the amount of ether is also getting reduced. So once all the ethers will be exhausted of a particular contract, then contract will be invalid, because that contract will not be able to call another contract. As like transaction between user to user, similarly transactions can happen between contract to the contract. We have already seen these things, that each contract is being stored into the chain state database, where each contract is having its own wallet ID. So externally controlled account can call this contract account, and these contract accounts are being called using this wallet ID. That is what the public address of a contract, same like the user address or user wallet ID. And for each of the contract there is a balance amount. So balance amount is showing, suppose a contract is calling another contract. In that particular case, contract need to spend some amount, same like the Ethereum transaction flow. So every time this balance will get reduced. Once it will become zero, then contract will be invalid, because that contract will not be able to perform any further transaction if the balance is becoming zero. Fine. Each contract is having its own hash value. So that hash value, so like this you can have the multiple contracts. The root of this Merkle tree will be stored into the internal state. So that is why it is, this is how it is providing the immutability feature. So this is one of the like example of smart contract, that how it can help in real world. So if you see the concept of the product team, they are sharing that project. To execute project, they require the money from the supporters, and they are collecting the money from the supporters until the goal is reached. So in that case, obviously supporter will not directly pay to the product team. There should be some third party involvement, which is the like current process where agreements are happening between two people. In this particular case, what will happen? Suppose they are taking the, both of them are trusting on the Kickstarter, that is the third party. So Kickstarter will collect the money from the supporters, and that money will be transferred to the product team. So here, first of all, it will create the trust issue, because the assumption is that they are trusting on Kickstarter. It may be possible that supporter may be worried that what will happen to that fund, whether it will reach to the product team or not. Similarly, product team will also be completely dependent on that third party. So there are certain issues. Along with that, this third party will also have their own service fee. So the cost is also being increased. In such kind of applications, smart contracts are helping, where supporters and product team will meet. They will mention their terms conditions, and that terms conditions will be converted into the code, which is executable code, and that code will be deployed on the blockchain. In this case, what will happen? Supporters will donate the fund to the contract, and contract will store, as I mentioned, that smart contracts are having these, can store the values. So the supporter teams, whatever money they are donating, that will be stored into the smart contract. It will not reach to the product team immediately. So until within the given timestamp, if the goal is reached, that this much amount of money is collected by the contract by this time. If the goal is reached, then it will be forwarded to the product team by the smart contract. If the goal is not reached, then it will go back to the supporters. So here, whole process is done by the smart contract, and as smart contract is immutable, so both the parties will have the trust building mechanism. This is another example. Generally, we are seeing that people are going for renting the house. So they are going to I can say third party to prepare the agreement. Or like, let's say purchaser who is purchasing a land from someone, they must have to meet the intermediaries, and they are writing the paper-based contracts. Fine. In that case, there is lot of trust issue. So what we can do here, that these parties agree on a particular contract. That contract will be written in the form of the rules or functions. Based on that, once the contract is written, it will be stored into the blockchain. But the major risk here is that code will remain the vulnerable and can be corrupted. So those vulnerabilities and security risks we'll see later. Again, immutability feature is also posing the security risk here. Because once contract is deployed on the blockchain and as it is deployed as a form of the blockchain transaction, it is immutable. So if that contract is having error, which you cannot correct it, and then that error will propagate to the further transactions. So at that time you need to come up with the new contract transaction and then you have to execute. So immutability feature is one side, it is helping to build the trust between the parties. But at same time, vulnerable code, if it is written and deployed over the blockchain, then it is difficult to recover back because it is having the immutability feature. So these are the benefits of smart contract. So once the contract will be deployed on the blockchain, so it is in the form of blockchain transaction. So contract means code will be immutable. Nobody can modify that code. Again, contract is distributed. So if I'll talk about the scalability, if you see that two-party contract, paper-based contract, there are a lot of terms and conditions between two parties. If third party will be involved, then again it will become more complex. Fourth party will be involved, again it will become more complex. Like this, if the number of parties will grow in the contract execution, I'm not talking about smart contract, I'm talking about the physical contracts, where it is creating more complexity. But here the smart contract is just a code which is deployed on the blockchain. Everyone is having the access. So it is reducing the complexity of the contract execution, being a smart contract. Also it is allowing the direct dealing with the customers. So there is no disputes. They need not to rely on the intermediaries or third party. So it is offering the direct dealing. Again, but during the dealing between two parties, they should mutually agree on their terms condition. There should not be an ambiguity. There are certain cases where the party is throwing condition, but that condition context may be different. Those contexts are difficult to bring into the contract because it is just a code. So whatever it is written in the form of code, it will execute. Later party will not be able to say that I put this condition based on this context, not other context. So interpretation should be unambiguous while writing the contracts. It is having the resistance to failure. If I'll talk about the software-based contract or paper-based contract, on software-based contracts, there may be high possibility of that attacks can happen and anybody can update the contents. Similarly, paper-based contracts, it can tear down, it can be lost, or it can be modified. Fine. Trust. Smart contracts are building the trust among the parties due to such security features, because it is having the transparency that how transactions are happening, it is having the tracking, and it is having the immutability feature. Fraud reduction. It is difficult, I can say, frauds cannot happen on the smart contracts. Nobody can manipulate the contract's terms condition because it is in the form of the code. Cost efficiency, as already we have seen that as it is removing the intermediaries, so cost is less. Cost is not in terms of money, but time complexity is also less in case of the contract execution as compared to the paper-based contracts. Record keeping. Contracts are having their own internal storage, so all your records can be stored over the blockchain or within the contract for the particular. So on contract, if you are storing the value, so whatever time limit is defined, Based on that, up to that time limit, your records will be stored. Similarly, all your transactions are being stored on the blockchain. So it is very easy to track such records. But coming to the security risk, there are various security risks of the smart contract which need to be taken care before utilizing such services in the any application. So if I'll talk about any smart contract, which should not be poorly written contract. Poorly written contract means it should not have any loophole. So already we have seen that whenever application softwares are developed, it can have buffer overflow, underflow. There are various vulnerabilities exist. Those vulnerabilities should not come in the contract. So before deploying the contract, such code should be tested and verified properly. If it is not tested and verified properly, and if it is having any loophole, adversary can take advantage of such vulnerability and can attack to the contract. So that attacking contract may be due to stealing the money from, the contract itself, may be affecting the behavior of the contract. So there may be different goals of an attacker while performing such attacks. So in this paper, the attacks are considered into the 4 categories. One is the malicious act. So you know already there are viruses, malwares, phishing attack, fake exchanges. Such viruses are trying to steal your confidential information on the blockchain. Let's say password. Say if my wallet key is stolen, then you can lose your account. So these are like malicious act. Second thing is the weak protocol. Although it is mentioned it is a weak protocol, if I'll take the example of proof of work. To confirm the transaction, you require the confirmation from the to update the transaction on the blockchain. You require the confirmation from the 51% of nodes. Now think about, if adversary is able to manage to create 51% of nodes in a network, or if 51% of nodes are working for an adversary, that is practically difficult in case of public environment or public chain, but still there is a risk of the attack where adversary will have control over all the transactions, adversary can modify all the transactions, adversary can update all those transactions. So these are the weak consensus protocol which is being implemented. Already in one of the lecture, Professor Roman has covered that selfish mining, vector 76 attacks. Such attacks, or I can say double spending, all these attacks are happening due to the weak consensus protocol. Coming to the defraud. So I'll take the one example. On Bitcoin, it performs the 6 transactions per second on average. Now see, I am the buyer, you are the supplier of a product. I have done the payment to you. I cannot wait for the confirmation of those 6 transactions. As I have paid immediately you, I will obviously expect the product from you. So I will force you to send me product. So you will send me the product before the confirmation of those transactions, and immediately I will execute the withdraw function. Fine. So it may be possible that suppose if I am having the 2 transactions, one transaction is about payment to the supplier, another transaction is withdrawing. Suppose if I am executing the second transaction, one transaction is already floated, but miners are choosing the transaction 2 to confirm. That is the withdraw amount. So what will happen? That payment will not reach to the supplier, but product will reach to me. Such frauds can happen due to the, I can say, delay in the transaction confirmation. Because no, I can say, buyer will wait for the payment transaction. They will immediately expect the product. Coming to the application bugs. So smart contracts should be code free, bug free. If loopholes are there, it may lead to the unexpected behavior of the contract. It may allow an adversary to steal the money from the contract itself. It can allow to manipulate the other users or impersonate the other users. So based on this application bugs, we'll see the different types of vulnerabilities. So Open Web Application Security Project, every year they are declaring the top 10 smart contract vulnerabilities. That is depending on the number of cases happened or number of times that vulnerability is being exploited, and accordingly they are listing in that project they are listing the top 10 vulnerabilities. If you see in 2023, from 2023 some of the vulnerabilities were being removed in 2025. That is depending on the number of times that particular vulnerability is being exploited by the users. So based on that report, in 2025, these are the vulnerabilities, top 10 vulnerabilities are considered on the for the smart contract. So we'll see each of the vulnerabilities one by one. First vulnerability is about the access control vulnerabilities. Suppose if you are writing a code like this, in this case, it is allowing unauthorized user to access that particular function because there is no any access mechanism mentioned. So in this case, if you say that function burn, which can allow anybody to access that particular function, actually if I want to withdraw the amount, I should only be able to withdraw amount from my pocket or my wallet. But this function will allow anyone to withdraw the amount. So it may be possible that adversary can initiate this or trigger this function, can withdraw the amount from anybody's account. This is the bug. So how it can be solved? Because here there is no access control mechanism available. One solution is there. Initialization function can be called once, and it should be from the authorized parties only. Second is that role-based access control you can apply. That whoever is initiating that particular function, their role should be verified, whether that person is allowed to or whether that user is allowed to withdraw that amount or not. Third thing is that in smart contract, you can mention the ownable or you can make public only owner. So only owner of that particular wallet will be allowed to burn amount. So this is like solution. So when you are writing the contract, you cannot make all the contracts as a public contract. You must have to see the logic behind that contract, or what is the goal or intention behind writing that contract, and accordingly you can invoke those functions or you can write this function. So the solution mentioned here is that you can use the ownable features of the contract, and only you can make only owner can withdraw that amount. So this vulnerability is called as the access control vulnerability. There is no fine-grained access control available currently. So while writing a contract itself should invoke or apply the fine-grained or role-based access control. Similarly, price oracle manipulation. Many times your business logic is dependent on the external input. That is called as the oracle. So there are many examples where the particular rate is dependent on the external rate. So if external oracle is being attacked, attacker can affect the external oracle to update the rate value. If you see in this particular example, there is a interface iPrice feed. This interface is giving the price update. Fine. To this particular contract price oracle manipulation. So if you see here, price feed is giving the latest price. Now if latest price is modified in a oracle, not in the contract, because in contract you cannot modify anything because it is immutable. But when it is interfacing with the external feed, and in external feed that source is being manipulated by an adversary, you will get the wrong input in your contract. Fine. And here attacker can manipulate the oracle, and they can borrow more than they should. Ultimately what attacker can do, attacker can modify the oracle values, because the oracle security is also different. It is means it is not like having the immutable feature. It is taking the external input in your contract. So all the business logic you cannot give like in the form of smart contract. Some business logics are depending on the real-time environment. So here real-time environment data you need to take to execute that smart contract successfully. So real-time data are available in certain databases. Those databases should also be secure. Otherwise input will be changed, input is going to be changed in the external database, and that input will be the wrong input in your case. Fine. So how you can solve this? Instead of getting the value from this single source, you can perform the data aggregation and compare the data value, and you can come up with the actual value or price feed in this particular example. You can define the minimum and maximum value. If you go back, here what it is checking, price should be greater than 0. This is the only thing checked. So it can be any price. Suppose let's say particular product price is 20 rupees. And attacker is successful of modifying the price oracle. And instead of that actual amount, attacker is saying that attacker is modifying that value and showing it is like 25,000, 50,000. The contract owner or any other user can earn that much money by modifying the external oracle. So in this case, you can define the minimum and maximum value. The latest price value should not be more than this value and should not be less than this value. Okay, so you need to provide the condition. So when you are getting the price feed, in this particular case, when you are getting the latest price, it should be checked for the minimum and maximum price. So that even though if adversary is able to successful of modifying that value, but adversary will not be able to perform drastic change in that value. Fine. Then time lock for price update. You apply the time lock that for this particular duration, the latest price should be this much only. So this should be implemented at the feed level, price feed level. The price locking should take place. So that even the adversary trying to modify, but lock price will be taken at the smart contract level. And you can apply the cryptographic technique where your price value should be in encrypted form or it should be in the hash form, so that integrity of the price feed can be maintained. But such attacks can happen due to the interface with the real-time data, where a smart contract is requiring some real-time input data. Then logic error. If your code is not written properly, it may distribute the reward to in unexpected way. It can perform the improper token minting. And lending pool, where your overall money is there, lending pool imbalance can take place. Here attacker can try to steal all the money from the lending pool. If I'll show you here there is a faulty calculation because it is incorrectly reducing the user balance without updating the total lending pool. Suppose here if you see the withdraw function, user is withdrawing that value. In user balance that amount is being withdrawn. In user wallet amount is being withdrawn. But in lending pool where total amount is there this deduction is not taking place. Ultimately what will happen? If I'll collect let's say 10 wallets. In 10 wallets it will have less money. Actually what should happen? 10 wallets total sum should be equal to the lending pool value. So in this particular case, a lending pool value is not being updated, it will create the imbalance between lending pool and the user wallets. Actually this should update the total lending pool, but it is omitted here. And this will allow an attacker to keep the lending pool value as it is. But withdrawal is taking place. So if I am the user or I am the adversary, I can take the advantage of such logic error. Every time I will invoke this smart contract and I will withdraw the amount. But still sufficient amount of balance is available in the lending pool. Still sufficient amount of balance is available in lending pool, because lending pool we have not reduced that amount which we have withdrawn. Fine. So ultimately it will lead to the what? Creating the more tokens, which you can like infinite of tokens you can just withdraw. Your lending pool is not being updated. If this vulnerability will be there, tokens will be generated, which is will be tokens are as it is, but every time withdrawal taking place. So the total value of number of wallets will not be equal to the initial lending pool value. Fine. So such imbalance should not occur. So your contract should be tested towards such errors also. So how you can solve this error? Whenever you are withdrawing the balance, or whenever smart contract is withdrawing this balance, user balance is getting updated. At same time, same amount what you have withdrawn is taking place from total lending pool, that value should also be deducted, so that imbalance will not occur. Coming to the lack of input validation. So if you see here, for this particular amount, the data type is unit 256. Here user's input should also get validated. If it is not validated, so the function is set balance, address user, unit amount. The function allows anyone to set the arbitrary balance. So suppose if I am invoking this function, in that case I can set any balance, because my input is not verified. Whether I am allowed to set that balance, whether I am having that balance, that should be checked. So input validation should be taken care. If this validation is not taken care, anybody can set my balance. So that is leading to the access control. Coming to me, I am having, suppose let's say, access to my balance. I can set any balance. So here you need to see that modify only owner. Only owner should be allowed to set that balance. Not anybody should be able to set my balance. So it is showing that message sender should be the owner. If message sender is the owner, then and then only message sender will be able to set the balance. Otherwise, so such errors may cause like arbitrarily setting up the balance in any of the user's wallet. Another vulnerability is the re-entrancy, in which the same call will be being called again and again without updating the user's balance. So if you see the function withdraw, where whole amount is being withdrawn by the user, but the balance is not being updated. If you see, the balance is being updated later after sending the value to the particular user. So once the user is invoking this withdraw function, the amount is equal to balance, and amount should be greater than 0. Fine. But here balance of the sender is not updated by the 0. So ultimately what will happen? This function can be invoked continuously by user, because balance is not made 0, so continuously user can withdraw the amount. Actually it should be 0 while sending the balance. So this balance of the sender should be equal to 0, that should come here. So this bug can be fixed, like update the user's balance before sending ether balance. So before sending the balance ether, you should update the balance value. So it is like I am just creating the deposit in your account. At same time I am invoking the withdraw. Whatever deposit I have done, that should be deducted from my account. But if it is not being deducted, every time I can deposit money in your account. Fine. So, and at same time that contract should not be interrupted also. Otherwise, deposit transaction will go, but deduction is not taking place. Uncheck external calls. we have already seen that a contract can call another contract, or a contract can call another function if that function is not successfully completed, or if that return value of that function is not checked. What will happen? The called contract is failed. Calling contract will believe that it is already successful. In that case, such states are not maintained. So suppose if I am transferring the amount to you, so that is the calling function. I am transferring amount to you. I can transfer amount in two ways. I can invoke the transfer function, or second is I can send the message in the blockchain transaction. And if I am not checking the return value, state of that particular invoking the function, it may be possible that called function can be failed. If it is failed, on transaction, it will show that I have deposited amount to you, or I have transferred amount to your account. But it is failed, so you will not receive that fund. But in my case, what will happen? I have deposited. Fine. So state should be checked. So you should always check the return value of send and call function. So such mechanism should be implemented in the smart contract, and the return value of send and call function need to be checked. So you can use the transfer instead of the send, because the transfer can revert the transaction if the external call is failed. If the external call is failed, transfer will revert the transaction. But if you are using the sending is for message, in which case called function, calling function will not check for the status of that message, whether it is being received or not. Flash loan attacks. Whenever you are having the atomic nature of the blockchain transaction, in that case, all the operations must succeed or they fail. So all your transactions will be within particular that single transaction. So it will borrow the large sum of funds without the collateral within a single transaction. So here I can connect such transaction with the re-entrancy attack, because we have seen that through re-entrancy attack, adversary can steal the fund from the contract. You can perform the oracle manipulation and you can steal the fund, or you can apply the faulty logic to get the fund. But here the quantum of fund releasing or stealing will be more, because all your transactions are what? Within the single transactions. In previous cases, such attacks are affecting to the particular transactions, not all the transactions. But if you are having the, if atomic nature of the blockchain transaction is applied, in that case, at a time you can hijack or steal large amount of fund. By using the vulnerabilities like oracle manipulation, re-entrancy, faulty logic, sorry, integer overflow and underflow. If you see here, there is a data type for value is the unit 8. That means that data type is having the 8 bits value. So, and it is unsigned integer. So it can produce how many values? From 0 to the 255. If it is signed, then minus 128 to the 127. Fine. So if my value is going beyond this value, if my value is going beyond this value, again it will go back to the 0. You can recall the data types in the C language. The data type unsigned integer is having the 8 bit, which is ranging from 0 to the 255. And here if I am balancing a balance value, I am updating by the value. Every time I am adding that value. If that value is going beyond this data type limit, what will happen? It will again come back to the 0. Similarly, if you see the decrement of that value, here the value balance is decremented by the value. So if it is going less than 0, it will again go back to the 255. By using such loopholes, adversary can manipulate this value. Adversary can affect the behavior of such contract. So Actually, Ethereum Solidity 0.8x automatically checking or taking care of the integer overflow and underflow. So whenever you are using the functions like add or some value, or you can subtraction of the values like let's say withdrawal. So such function, during such functions, this vulnerability is taken care by Ethereum Solidity 0.8x. Fine. Insecure randomness. You know that randomness is widely used in the gambling, game winner selection. Because there numbers should be produced which should be unpredictable. But in theory, we have already seen that true random numbers are very difficult to generate. And on blockchain, the random number generation, because if you are having certain gaming applications where you require the random number generation, it is very difficult to generate the random numbers. So it is using the pseudo randoms. Pseudo randoms are based on the or dependent on the certain inputs. You need to provide some seed input. It will apply the mathematical function, and every time it will generate the new random numbers. Okay. But true, it is not, it can be predictable. If your seed value is predictable, if your seed value is predictable, it can be predictable that what will be the next random number. But when you are having gambling, game winner selection, where it should be the fair game, nobody should be able to predict that random number. Fine. But on Solidity, you cannot afford to do the complex calculation for the pseudo random number generator. So generally random numbers are being created by using the block data, block timestamp, hash value of the transaction. By taking such inputs from within the block, it is generating the random number. But this is again insecure method, because all the blocks are visible to everyone. And adversary can be successful of predicting the next random number. In such cases, such games will be failed. And if such games are involving the high amount of money, because it is giving the unfair advantages of the people, if people are performing such analysis. Denial of service attack. In this case, adversary's goal is to exhaust the resources, because if all your guesses are exhausted, you will not be able to perform the transactions. Similarly, CPU cycles or storage. Let's say, forget about the smart contract or blockchain. Suppose in your email, I am sending the large amount of data continuously, which may not be useful to you, and you are not automatically deleting those data. I am sending large amount, your storage will be exhausted. After that, you will not be able to receive any further message from any of the user. Because everything in a blockchain also, on blockchain also, everything is limited or constrained by the resources, whether it is a gas, CPU cycle or storage. So adversary's goal is to do what? Exhaust such resources, so you will not be able to avail blockchain services. So there is an attack, gas exhaustion attack, where malicious actor will create the transaction which will require the high amount of gas value. So if you see the re-entrancy attack, which is exploiting the contract call sequence to access the unauthorized fund. So I'll continuously access that unauthorized fund. Ultimately what will happen? Fund will not be available. So genuine users will not be able to perform transactions using that fund. So I can affect the balance value to the 0. Similarly in lending pool, I can make lending pool 0. Getting? So ultimately the goal of an adversary here is to exhaust the resources, so that genuine users will not be able to get the functionality of the blockchain. These are the certain attacks. Which are given in one of the paper, but all these attacks are based on the vulnerabilities which I explained in these top 10 vulnerabilities. As I mentioned, the immutable bug. If the contract is written and if it is deployed on the blockchain, obviously it is having the immutability feature. You cannot revert it back. And attacker can take the advantage of such immutability. And due to the impact of it, there is a decentralized autonomous organization. They have raised the fund approximately $150 million before the June 18, 2016. And attacker was able to manage to put $60 million under her control. And after that, to resolve that, hard forking is required, which is already covered, that what is hard forking. So that you can invalidate those transactions from whatever point you have performed the forking. After that, in main chain, all those transactions will be invalidated. But by that time, attacker was able to manage the $60 million from such contract. So it was like simple DAO contract, where attacker has introduced the Mallory contract. In this Mallory contract, if you see here, line number 5, where attacker is revoking the withdraw function. That function is calling withdraw function here in main contract. So Mallory contract is calling the simple DAO contract. In this, if you see the line number 8, the amount is being withdrawn. Amount is being withdrawn. But the credit amount, which is the total fund, I can say the credit amount, which is the total donation in simple DAO, was not updated. That means simple DAO is having the whatever donation is received by the simple DAO, which is as it is. But attacker is able to withdraw this function because this function was interrupted after the line number 8. Fine. So the this function can be called in repeated, and this loop will run until what? Whether the Mallory contract's gas is exhausted. Once the Mallory contract gas will be exhausted, Mallory contract will not be able to call this simple DAO again, or will not be able to call this function withdraw again. Or else call stack is full. There is a call stack limit. If call stack is full, then Mallory contract cannot be executed. Or balance of DAO will become 0. Balance of DAO will become 0. So here what will happen? Through Mallory contract, attacker was able to continuously call this simple DAO, and this DAO function was getting interrupted after this line number 9. Fine. Another example of immutable bug, where attacker introduced Mallory contract and attacker invoked this withdraw function same like attack 1. But what attacker did, attacker become the participant of this simple DAO. Attacker has deposited 1 ether in this donation. In this donation, attacker has deposited 1 ether, so total credit will be what? 1 ether. If only attacker is there. Otherwise, it is contributed by the number of users, not only by the attacker. So total amount is stored into this DAO. In this case, what happened? Attacker can call back that withdraw function. So attacker can withdraw how much amount? Maximum 1 ether, not more than that. But attacker took the advantage of this withdraw. First time when attacker withdrawn the amount, 1 ether, it was successful. Now attacker balance should become 0. That balance was not, attacker balance should become 0. Next time again, if attacker is calling that function in a nested loop, what should be the attacker's balance? 0 minus 1 ether. So it is reaching to the what? 2 raised to 256 minus 1 ether. You got it? Because it is not checking the limit. If attacker's balance is 0, the function withdraw should not be invoked. Even though attacker's balance was 0 and that call was called, this function call of withdraw was called in a nested loop. In this case, next time, first time attacker balance is becoming 0. In second call, attacker's balance will become 2 raised to 256 minus 1 ether. Because it will not produce the negative value. So, and such immutable bugs has helped the attacker to steal lot of money from such contract. Second immutable bug example is the Rubik's Cube, which is also well known, I can say, contract. But Rubik's Cube was renamed from the name of the dynamic pyramid was changed to the Rubik's Cube. So the developers, what they have done, they have changed the contract name. Generally, when you are writing a writing a program, you may be updating the what? Main function or main I can say program name. But you are not seeing that in which internal code, if you are missing that where this function was called. If same function is called again and again, everywhere you have to update the name of that function. But here if you see that constructor name dynamic pyramid was unchanged. So suppose if I am accessing this contract Rubik's Cube, but which constructor was called dynamic pyramid. And in that I can start performing the attack, or I can change the behavior of that Rubik's Cube. So Rubik's Cube behavior can be changed because the dynamic pyramid constructor, dynamic pyramid name was not changed in the part of the constructor. This is again immutable bug once it is deployed on the blockchain. Once it is deployed, then you cannot change it. So after deploying such contract, if you are experiencing the behavior of contract is not as per the expected behavior, again you have to start everything from the scratch, because you cannot modify the deployed contract. Fine. You need to change its address, because all the contracts are being called by their unique address. So if I want to introduce new contract will have the new address. Coming to the multiplayer game, in which keeping the private parameters in a code. All of you are writing the code in Java where you are having the private parameter, which is what it should be accessible to the only those particular users or within a function. Now if you see here, I'll first talk about the game. It is two-player game. Both the players will input some number. Let's say player 1 is inputting the number 5. Player 2 is inputting number 7. This contract will calculate the sum of these two numbers, 5 and 7. It is 12. If the sum of these two values, is the even, player 2 will be winner. If sum of these two values are the odd value, player 1 is the winner. So in such games, what is required? No player should see what number they are giving. Fine. And to be part of this game, they have to spend some ether value. So winner will get some amount, not complete the addition of because each player has to contribute what? 1 ether. So 1 plus 1, it is 2 ether. Whoever will be winner will get, let's say, 80% of that 2 ether. Because 20% of that total amount will go to the owner of that contract as a kind of service fee. That is why people are introducing or developers are introducing contract, and users can enjoy games, such gambling games. Fine. But if you see here in this particular case, player field is private field. So I can be player and I can see the transaction, that what is the bet from the player 1. And based on that I can adjust my value. Suppose if I am the winner based on the odd value of the sum. So I will say that if player 1 is adding the odd value, I will add what? I will input even value. So that sum will become odd. If player 1's value is the even, I will input what? Odd value. So I can have the access of the blockchain and I will wait for the player 1 to join, and I will see the transaction, what is its bet value. Based on that I can adjust my value, and every time I can win such game. Then ultimately the objective of that game will be failed, because it will give an unfair advantage to only one player. Another player will always lose in this particular case. Another well-known example is the governmental contract. So in this case, it is allowing participant to join the particular game. So this is like multiplayer game, not like two-player game, not like odd even game, which is two-player game. In this multiplayer game, the winning is decided based on the person or the user who is joining at the last will be the winner. Who is joining at the last will be the winner. But this is a time-bound process. In 12 hours, everyone should join. So it is kind of like fair game, because I will not know that at what time you are joining. And most of the users will try to join at the last, to become the last. And they will perform the transaction. That transaction timestamp should be the last timestamp. But at that time I can miss the deadline of the time. And I may not be participant also. So I cannot wait till last moment to become the winner. So in this case, and while joining I have to spend some amount. It is not like I have to spend only 1 ether. It is like if I am the first player, if you say the message value should be the less than the jackpot by 2. Initial jackpot value is the 1 ether. So if I am the first player, I have to spend what? Less amount. Because if you see the condition, message value should be less than jackpot by 2. So initially jackpot value is 1 ether. So if I am the first player, I have to spend how much? 0.5 ether. Then 0.5 will be added into the jackpot value. So it will become 1.5. Next player has to spend how much? 0.75. Third player. Like this every time. So whoever will be the last player will have to spend more money. But last player can win that game. Now you can understand this. Last player can win this game. So in this case, attacker can take the advantage of exception disorder or stack size limit. So here the stack size limit is the 1023. So attacker can run such mallory contract. So this mallory contract will grow that stack by performing the transactions. Mallory contract will grow the stack by performing this transaction. And as an attacker, what will happen? Once stack will be filled, it will start from the 0. Once the overall stack will be filled, it will start from the 0. So attacker will continuously grow that stack. So initially it will be 0, then 1, 2, 3, up to 1023. Again it will start from the 0. So at last moment of the 12 hours, no participant will be there. Attacker has grown that stack value, so that genuine users are not able to participate. Ultimately, even though they have participated, but at the end stack value will become 0, so no participant will be shown as a like participant. And when this line number 24 will be invoked, last investor will get this jackpot value. But there is no last investor in this case, because stack size is 0. The attacker is continuously growing that stack value. Fine. Ultimately, jackpot value will be always added. In next round, jackpot value will be more. Because in previous round, that jackpot value is not transferred to the winner, because there were no winner, no last investor. Fine. And attacker will wait for the particular time. It will grow the jackpot value. Will wait a particular time to become the last player and can steal all the money which is stored into the jackpot value. Fine. And this is happening due to the not checking the stack limit size. Coming to the unpredictable state, that is another attack on same contract of multiplayer game. An attacker as a miner can impersonate a miner. He can choose not to include each block in the transaction. I am having the block, but I am not sending to the, I am not sending that block into the blockchain. To be last player in the round, I can reorder the transactions. First of all, I will try to become the first player. So if I am the first player, I have to spend how much? 0.5 ether as per this curve, or less than 0.5 ether, not exactly 0.5. Condition is it should be less than the jackpot by 2. So initially jackpot value was the what? 1 ether. So 1 by 2. So I have to be, if I am the first player, I have to spend 0.5 ether. So here attacker will try to become the first player, and attacker will spend the 0.5 ether. And at the end, by playing the first and choosing the suitable amount of the ether to invest, attacker can prevent others to join the scheme. So if I'm spending more money initially, I can disallow other users to join, because other users will have to spend more money again. Where every time jackpot value by 2 is there. So jackpot value is being increased. So after performing this first attack repeatedly, jackpot value will become too large. And then if I'll run this attack, unpredictable state. So initial jackpot value will not be 1 ether. Why? Because that attacker has performed previous attack first. In that case, jackpot value will be too large, so no user will be interested to play that game. So no user will spend money, because the spending money should be what? Jackpot by 2. Fine. And because it is risky game, I can lose amount if I am not last player, so nobody will try to participate. In that case, once attacker is identifying that nobody is joining this game, then attacker will perform one transaction and attacker can get the jackpot value. Fine. Time constraint. Because see, such jackpot based game or multiplayer games are based on the timestamp, where you are choosing the winner is the winner should be the last player. An attacker as a miner can impersonate a player. Suppose he is managing to join this particular scheme on blockchain. To be last player in the round for a minute, to become a last player, he can play with the block timestamp. We have already seen one of the attack block withholding. I can hold the block, or I can do the selfish mining. I'll release that block at the last. Means I am playing with the timestamp. Or if I am able to change that timestamp, and I can mine in the off channel, not in the live channel, then I can release block with the delayed timestamp. If I'll release that block with the delayed timestamp, because I cannot release that block at the after the 12 hours, it will not be useful. So I will release that block with the delayed timestamp. So I can also be considered as a what? Participant. Fine. And like this, attacker can impersonate the other players by playing with this time constraint vulnerability. So these are the different, coming to the solutions. One of the best solution is that code should be written, it should be tested and verified. So you should apply the software verification tools, or I can say code verification tools. Before deploying, your code should be tested. Coming to the access control. In access control, it should be determined before deploying the smart contract on blockchain. It should be determined that who is allowed to access what, and accordingly code should be written. Coming to the oracle manipulation vulnerability, in that particular case, external values should be validated and verified. We have already seen that you can mention the min max value. Similarly, if I'll go back to the logic error, so you can apply the different state transition analysis. You can test that code before deploying, and so that such code should be logic error free or logic bug free. Fine. Input validation. Input validation should also have the access control. So we have seen that without validation, anybody is able to update the balance in this particular contract. In that case, input validation should take place. And who is accessing that particular function or a particular contract, that access control should also be there. Reentrancy. In reentrancy, state should be checked. State of the particular contract. So if I am performing the withdraw, the balance should be updated. If I am depositing, so state, I can say state checking mechanisms you can apply. Not on blockchain, but before deploying this contract, it should be checked. Uncheck external calls. Whenever one contract is calling another contract, return value should be checked whether that called contract is successfully executed or not. Similarly, integer overflow, underflow, which is already taken care, but still if you are writing a code, the post condition and pre-conditions it should be checked. That before updating and after updating, what should be the value of that particular variable. Randomness. There should be like secure methods that nobody can, but still it is a challenge. The pseudo random numbers should be based on the predictable parameters. Denial of service attack, so users' behavior should be monitored. And all these attacks like reentrancy, all this should be, I can say, patched. Then it will be difficult to perform the denial of service attack. So ultimately, as a conclusion of this lecture, all those smart contracts are helping a lot to implement the business logics along with the transfer of cryptocurrencies. But contracts themselves is coming with a lot of bugs and errors. So for any application development, first of all, contracts should be tested properly. It should be written properly. And after the successful validation of that contract, I'm not talking about the blockchain validation. After the successful verification and validation of that contract should be deployed. Thank you.